and welcome. So we are on the day first of week 6. So in the last class we started learning about symmetry adapted linear combination. So what is this essentially symmetry adapted linear combination? We started giving some brief example, but let's have a look at it in bit detail. So whenever in a molecule we have certain atoms, and each atom will have their own wave functions, and these wave functions are also looked at as orbitals. So different wave functions of different atoms will combine whenever they are energetically favorable and also symmetrically allowed. So what does that mean? So let's have a look at it. So for various metal complexes, the d orbitals they come into the into play. So it's not that two atoms having any two d orbitals can combine. So there are certain symmetry restrictions. So for example, if we have a look at the pictures that are shown on the screen, so two dz square orbitals they can combine, which is symmetrically allowed, and they can give rise to two molecular orbitals like this, okay, depending on which way they are combining. So they can give bonding and anti-bonding kind of orbitals, molecular orbitals. This set of sigma and sigma star that are formed out of the combination of two dz square orbitals, they form through a linear combination of those two dz square atomic orbitals. So here we have another example where either you can take dxz, two dxz orbitals, or two dyz orbitals. And so if you take two dxz orbital, and suppose this is my dxz plane and this is also another dxz orbital in the same plane, so they can combine. Okay, they can combine in two different way. One is in this fashion or another is in this fashion. So depending on that, you get either a pi bonding or pi anti-bonding molecular orbitals. So again, dx square minus y square can combine with dxz orbital because they are in the parallel plane. So they can have an overlap and you can form like a delta bonding. Okay, so delta bonding and delta anti-bonding kind of orbital. Whereas if you look at the right hand side panel of the screen, you can see that dyz and dz square, they cannot be combined because symmetrically they are completely different, and so is dyz and dxz and dx square minus y square and dxy. So because of the different symmetry of these orbitals, there will be no interaction. No interaction means no bond formation, right? So no bond formation means there is no resultant wave function or no resultant orbital formation. Now we need to find out that which are the orbitals in a given molecule that can form a linear combination to give rise to molecular orbitals, meaning the orbitals that are formed, they should comply with the symmetry of the molecular point group, right? So how to find that out? That we started with in the last class. We said that there is a tool called projection operator, and projection operator can give us the information about which are the orbitals that can linearly combine and give us symmetrically allowed molecular orbitals. So we stated in the last class that a complete projection operator is capable of generating a complete set of SLC. So what we did, we formed this projection operator, and we derived essentially, and this is the form of that projection operator that we formed using the general principle. And from there we also said that this is a special case when one talks about the purely diagonal elements of the matrices of a representation, and thereby this particular special case of projection operator will find out whether this phi t prime belonging to a particular jth irreducible representation occur within the orthonormal set, say phi i's, one of which is here as phi t. So, if you apply this projection operator onto any arbitrary function belong to a orthonormal set, then either this function itself will be this one or it will contain this function. In that case, this particular function will be projected out from that set by this projection operator, otherwise this function will be abolished. Or if this function contains this phi t prime and many other functions also, then all the other functions will be abolished and this one only will be projected. That is why it is a projection operator. So, you start with an Li dimensional set having orthonormal function and take them as basis, and you can construct the Li number of projection operator, and this complete set of projection operator can give you the total information about what are the particular function that can act as the basis of the whatever the irreducible representation one is concerned about. Okay, and in the molecular orbital picture, what you can think of that such a projection operator constructed from an exhaustive list of basis functions, a list of functions, and if you form all the projection operators, then the total set of projection operator will give you the overall symmetry adapted linear combinations that are possible. Now, this is about a complete projection operator. This term will be even more clear as we move ahead, and since we are talking about complete projection operator, there is also another something called incomplete projection operator, which is less efficient than this complete projection operator, where we deal with a complete orthonormal set and forming the projection operators involving the each and every element of the of any given representation, and so you get the total information about the SLCs. Whereas the incomplete projection operator, that is that deals with the the trace of the matrices that are formed while forming the representations. So, we will talk about that in a little while from now. So, this is the same thing that is written over the board, and we can write the explicit irreducible representation by replacing this generalized term J, right. So, here just for an example, we can write this as B3U. Suppose I am concerned about a particular character table of say D2H. Okay. So, and the function that you can choose as any of the bond vector, or you can choose as any of the atomic orbitals or anything. So, we know by now that the projection operator may be applied to an arbitrary function, say phi t, and only if that function itself or some term it in happens to be phi t prime, the result will be non-zero. If phi t prime is a component of the arbitrary function phi s prime, that will be projected out of it and the rest will be abolished. So, we have this term in this as a special case where we talk about the projection operator involving only the diagonal elements of the representations. So, t prime is a diagonal element, right. Now, ultimately this p t prime corresponding to a jth irreducible representation, that will project this phi t prime out of any arbitrary function as phi t. Now, if I what we started with, that Li number of or you can call it Lj number of orthonormal functions. Okay, so if you take a set of Lj number of orthonormal functions, then you can actually produce Lj number of projection operators, because using that Lj number of orthonormal functions, you can form an the number of diagonal elements that will be formed will be also Lj. So we can use that particular set of projection operators to completely find out you can use any general arbitrary function phi t correspond to any particular irreducible representation I, and the function that form a basis for the jth irreducible representation, which we termed as phi t prime j. Now how does the projection operator work actually? Okay, so before going into the exact formation of symmetry adapted linear combination, let's take a simpler example and see how the projection operator helps finding out that which of any given arbitrary function, which part of it actually form the basis for any given irreducible representation. Okay, so here we have an example where we consider the group C3V, and we take an arbitrary function which is as xz plus yz plus z square. Okay, so this is any arbitrary function. Now what we will try to do, we will try to get from this particular arbitrary function, we'd like to have a pair of functions which will form the basis for the irreducible representation E, that is two dimensional irreducible representation that C3V point group has. We would like to find two functions which we would like to take out from this arbitrary function xz plus yz plus z square, and that those two functions will act as the basis for the representation E. Now here we have all the matrix representation of all the symmetry operations that C3V point group has. Okay, this one we have already dealt with earlier, so must be familiar with you. Now here we are talking about a complete projection operator, right? So when I talk about complete projection operator, I will be always dealing with the matrix elements. Okay, so matrix elements are specifically as a special case, we will take always the diagonal element because that serves our purpose. Now what we have to do? So we have to first form the projection operator. So projection operator has the form that you can see on your screen over there, right? So you have to find out the dimension of that irreducible representation. So here for representation E, Lj will be equals to 2. H for C3V, it will be equals to 6 because it has order 6. Then you have to get the matrix elements. So this is a representation, and it essentially we are taking the elements of that representation. So here we have shown on the screen that each and every every symmetry operation has their matrix representation. So they are 2 by 2 matrices, correct? So now you have total 2 diagonal elements in that each and every matrices. So what you have to do, you have to select first the 1 1 element, because for any given matrix which is 2 by 2, so you have say A, B, C and D. So this particular one is essentially termed as 1 1, okay, 1 2, 2 1 and 2 2, right? So that's how in matrix algebra we term this, we use the terms. So what we have to do, we have to find out this T prime, right? The matrix projection operator form for this Pj T prime diagonal elements. So we will be concerned with this one and this one. So here it's a two-dimensional matrix, and we will be two-dimensional irreducible representation because we are concerned with E. So therefore, we have two projection operators because we have two diagonal elements. So first, what we have to do, we have to form the projection operator for this term 1 1 and apply that on the function that we choose. So here we have like xz plus yz plus z squared, that's an arbitrary function. So we have to operate this projection operator corresponding to this 1 1 element onto the arbitrary function xz plus yz plus z squared, and then again we have to form the projection operator involving the term 2 2, matrix element 2 2, and again do the same thing. So we will get two functions out, okay, when we operate these projection operators, these two projection operators on this arbitrary function. All right. So what we have to do is written here. So first we are dealing with this P11 term, correct. So if you can correctly identify this this symbol P superscript E and subscript 1 1, and you can correlate with the general form that we have earlier used, let's say Pj T prime T prime. Okay, then you are fine. If you have any difficulty, you go back and again check the previous part that we have talked about and then come back to this portion again. So now we are going to operate this projection operator on this arbitrary function xz plus yz plus z square and see what it gives out. Okay. So in order to do that, what we have to do, we have to get the form of this projection operator that I just said. So Li is 2, J is H is equals to 6, and then if you look at the form of the projection operator over there, you get the matrix elements corresponding to a particular symmetry operation, right? So you start with say E, then you go for C3, then you go for C3 squared, then you go for sigma V xz, sigma V prime, sigma V double prime, in that way. All right. So you see how we have done this one, that how did we operated this projection operator on this function. So Li by H is common for all, and then you have selected the matrix element. So here you see this is for the first term is for identity operation. So here we have this term 1. If you quickly go back, you will see this 1 1 element of the operation E is 1, all right, and then you need to know how this identity operation changes the function, right? So E doesn't do anything, so x remains x, y remains y, z remains z, and then overall the function xz plus yz plus z square remain as such. All right. So that therefore you have the multiplication by the matrix element term, that is 1, and then whatever is happening to the function due to the application of the symmetry operation on that function. So it returns the same one. Now you move on, because you have a sum over all r's. So you have to keep doing for each and every r, that is symmetry operation, and then altogether you have to add. So I have just told you about the E. So next step you have to go to the next operation, that is say C3. So here on this table you have all the transformation property, this particular table you have all the transformation properties of x, y and z axis upon this symmetry operations, okay, for C3V. So these are the transformation terms, and at the end you have actually the overall transformation of the function xz plus yz plus z square. So what you can do, you can verify this table yourself, okay, and I will suggest you to do so. So here coming back, so what we have to do, first we have to find out the 1 1 element for the C3 operation. So let's quickly go back to this one, and C3, the 1 1 element is minus half, all right, and let's look at this. Yes, so we are first multiplying by minus half, and then it will be multiplied by the resultant of the operation of C3 onto the function xz plus yz plus z square, and this particular term that is given here is it can be found over here. So you can see that is this particular part, right? So in that way you keep going for C3 square and sigma v and sigma v prime and sigma v double prime. So when you complete this sum, you have got your result for the operating projection operator on this arbitrary function, and this projection operator is specifically for the irreducible representation, which is two-dimensional irreducible representation corresponding to the C3v point group. So after you get that sum, what you will get, you will get some terms with containing xz, some term containing yz, some term containing z square. So ultimately if you can rearrange them properly, so you get the coefficients corresponding to xz, coefficients corresponding to yz, coefficient corresponding to z square, because these three terms are there in my arbitrary function. So my intention will be to rearrange the result of this projection operator on this function to also express as coefficient of these three functions individually, components individually, xz, yz and z square. So that's what is shown here. So when we collect all these terms and separate the coefficients, then I get the coefficient of xz to be 1, while the coefficient of yz to be 0 and that of z square to be 0. So my projection operator P11 corresponding to the irreducible representation E for C3v is projecting out xz as the basis for E representation out of the arbitrary function xz plus yz plus z square. Alright. So we have to get the complete result by using the all the projection operators that can be formed explicitly, because we are dealing with the complete projection operator. So the next projection operator will be taking the other diagonal element of this 2 by 2 representations. So that will be correspond to the 2 by 2 diagonal element of each and every symmetry operations. So if we just quickly look at the representation for E, the 2 by 2 element is also again 1, so it will be no different, and for C3 again it is minus half, for C3 square minus half and so on. So you get those particular element out, okay, and then multiply that with the resultant of the symmetry operation on the particular arbitrary function. So in a very similar way, when we do it and ultimately you collect all the terms and find out the coefficients, we get the coefficient for yz to be equal to 0, is equal to 1, and the rest of the two that is xy and z square, they give us 0. That means when we apply P22, it projects out this yz that can form the basis for the representation E. Okay. So now if we compile the total result, that we have a complete set of projection operators, meaning P11 and P22 for the representation E. Altogether it is giving us xz and yz. So this means that xz and yz out of that arbitrary function xz plus yz plus z square can form the basis for E, which is not surprising, right? Because E is a two-dimensional representation. So we will have two different functions acting as a basis. Okay. So this one will be xz. So xz and yz will form the basis for representation E. And also you see that z square is completely abolished by this projection operator. So it will tell you exactly that which are the functions that can form the basis of any particular irreducible representation, and whichever is unnecessary, that whichever do not form the basis for the particular representation, they will be automatically abolished. So you will get a zero result when you operate projection operator on the function for that particular component all the time. So here z square gave zero contribution in both the cases for P11 as well as P22. Okay. All right. So that is about the complete projection operator. So now this complete projection operator, it deals with the the diagonal elements. So for a one dimensional representation, things are easy, because for one dimensional representation the matrix is also one dimension. So it's kind of trivial. But the moment you go for higher dimensional irreducible representation, say 2 dimensional or 3 dimensional, things become a bit complicated, because getting the matrix representation, finding the particular elements and then doing it, it is quite cumbersome, and it cannot be finding this complete set of projection operator. It's not really can be done by a machine alone. So it needs so-called human intervention. All right. So it will be like someone dealing with this problem has to construct the computer to compute the total projection operator and its effect on a particular function, and then again go for the next one. So every time someone has to instruct it continuously, and altogether it's really cumbersome. But getting the character of the representation is always easy, because you have the character table already. So you just have a look at the character table, you get it. And ultimately what you are doing, if you think about, so you are taking any representation, whatever the dimension be it, and you are just taking the diagonal element to form the projection operator, right? And then collecting all the diagonal projection operators corresponding to all the diagonal elements, you are forming the total set or complete set of projection operator, which is known as complete projection operator. Now if you look at this one, if you look at the trace of the representation, that actually contains the information that can be found from each individual diagonal element that we have already talked about, and that's why this trace is also called the character. So it should be pretty fine if we take the character and try to form a a projection operator out of that. So in some sense it will be incomplete, but it will be extremely useful. Now it will be incomplete when we particularly go for extremely complicated irreducible representations, but otherwise for actual and practical purposes, this incomplete projection operator, which involves the characters only, should work absolutely fine. And in the next class we will talk about this incomplete projection operator, and we will try to derive this incomplete projection operator and use it, and we will try to validate the points that I just discussed. Okay, so we will stop here today, and following class we will discuss more about these things. Till then, have a good day.